I'm Takumi Ishibashi from Okayama University of Science, Japan. I will give you the presentation entitled Analytical Model for Accordion Motion for Pipe Inspection Robot using Extension Type Flexible Pneumatic Actuator. Next, I will show you outline of my talk. This is outline of my presentation. First, I will explain the background and purpose of our study. Currently, it needs to develop pneumatic drive robots that are flexible slim and capable of operating in hazardous environments. In order to inspect pipes inside water pipes and nuclear reactors. Therefore, in this study, we focused on the snake's slim structure and its ability to move through pipes using accordion motions. We aim to develop a robot that can travel inside pipes by coiling and extending. Also, the target robot became a straight shape and has no pressure for easy to retrieve. In general, the inner diameter of pipes that have deteriorated over lifetime will become narrower. Therefore, it is necessary to use the inspection robot that is significantly thinner than the expected pipe diameter. In ideal, taking into consideration of obstacles and easy retrieve, after pipe inspection, we aim to develop the robot that is one-half to one-third the size of expected pipe diameter. In addition, to prevent huge cleaning costs, it is better to make the robot low cost so as to be disposable it. Next, we introduce previous research on pipe inspection robots. The left photo shows a connected wheel-type pipe inspection robot developed by Ritsumeikan University. This robot is equipped with multiple zigzag rings, and its wheels are pressed against the inner wall of the pipe by springs attached to the joint. The robot can travel not only in horizontal but also in vertical pipes. The right photo shows an earthworm-type pipe inspection robot developed by Solaris Inc. The robot can realize the head-started motion, such as an earthworm, and travel in pipe by using pneumatic artificial muscles. The robot can travel in relatively small pipes with an inner diameter of 16.5 millimeters. Next, we introduce another inspection method that does not use robots. That is fiberscope inspection. The fiberscope is particularly suited for inspecting buried pipelines, such as water supply pipes. However, fiberscope inspection has limitations. In detail, the inspection distance is restricted due to the limited number of pipe bends that the fiberscope can navigate. The disadvantages of the previously introduced method can be summarized as follows. First, wheel-type robots that use motors are difficult to operate underwater. Second, for earthworm-type robots, the range of pipe diameters they can travel is constrained by their initial diameter. Third, fiberscopes are not suitable for inspecting complex of branched pipes, and retrieving robots or fiberscope from long or bent pipe can result in significant flexible resistance. Therefore, in the previous study, we proposed and developed a new robot that could be operated underwater, flexible enough to apply in various pipe diameters, and easily retrieved after inspection. It is report. In this report, we propose an analytical model of the robot to calculate its motion to design the robot. Next, I will briefly introduce the construction and operating principle of EFPA. The left figure shows the appearance and construction of EFPA. EFPA consists of a silicon rubber tube covered by a nylon sleeve, bellows-type nylon sleeve, and end connectors. The operating principle of EFPA is as follows. When supply pressure is applied to EFPA, the internal rubber tube expands toward various directions. As the bellows restrict the expanding direction, the EFPA expands only in the axial directions. Next, I will introduce the fundamental device of the previous robot. The figure shows the appearance of the EFPA with the wire restraint as a proportional restraint in the axial direction. It uses PET plate with thickness of 1 mm as a wire guide, like this. A wire winder device was fixed to the end of the EFPA. The wire was fixed to another end of the EFPA. The wire also passed through a small hole in restraint plate. It can change the behavior of the prototype by twisting the restraint. The left figure shows the transient view of motion of the EFPA with wire winder restraint when stepwise pressure is applied. The table shows the position of restraint plates and wire setting angles. The operating principle of this actuator is as follows. When the EFPA extends, the pre-pulling force of the wire winder becomes greater than the stretching force of the EFPA. So the EFPA bends towards the wire. As the stretching force of the EFPA increases, the actuator stretches in the axial direction. The left figure shows the transient behavior when a stepwise pressure of 500 kPa is applied. When the EFPA begins to be pressurized, the pulling force of the wire is small and the EFPA stretches linearly. As the wire displacement and tension increase, the actuator bends towards the wire restraint side, as shown at time 0.39 to 0.59 s. As the internal pressure of the EFPA increases, the extensional force of the EFPA increases and approaches the wire tension, and the curvature of EFPA decreases and became arc-shaped as shown in after 0.75 s. We would like to control the behavior for designed motion. What's the method to obtain the desired motion? We propose the analytical model of EFPA with wire winder restraint. This model is developed based on its behavior. The left figure shows the coordinate of EFPA and the numbering of the constraint plates. The middle figure shows an analytical model of the EFPA situated between two constraint plates. For convenience, it is assumed that the bottom edge of the EFPA lies on the horizontal plane in a coordinate system. The rear edge has been aligned horizontally using a coordinate transformation. The following assumptions are made in constructing the analytical model. The restraint wire does not stretch. The EFPA is bent along an arc shape. The first, the first restraint plate set towards 0 degrees or 180 degrees. The bending directional angle is 0 degrees. In the next step, from the left figure, we can obtain the following equation from the geometric relationship. Ri is the radius of curvature, and d is the length 10.3 mm between the EFPA center line and the restraint plate wire. For simplicity, the bending angle beta I is obtained using equation 1 and 3. This figure shows the transient response of the extension ratio of the EFPA center line, LE equals sigma LEI. This is the center line length measured from experiment. This response includes the dynamic characteristic of the control valve of EFPA. RT is the inner diameter of the rubber tube, 5 mm. However, since the rubber tube expands when EFPA is pressurized, the force generated is calculated using acquisition force. Left upper and lower figure shows the relation between displacement and pulling force of rubber tube in EFPA and wire winder respectively. From both from both figures, we can see that force Fc and force Ft change depending on the displacement of the EFPA. From these results, the relationship between force Ft and displacement x and the relationship between force Fc and displacement x are approximated as follows. Furthermore, we propose the following simple empirical analytical model from the response of the EFPA. From the left figure 1, the response of wire length according to time is approximated by equation 7. The equation was determined based on the response of the center line length. Linear approximation was made between 2 points. 1. 0.50 seconds, that is when the center line length begins to change. 2. 0.8 seconds, that is when the curvature became extremely small. Expressing this generally, it became equation 8 and 9. AC, large TE, small tde, and large LC are the time coefficient, the time constant, and dead time, and when the wire winder length, respectively. If these values are known, the bending angle beta I between the restraint plates can be obtained using equation 10. In equation 10, the relationship between large LEI, large LCI, and large LE, large LC is as follows. Large LE0, Li, and large L0 are the initial lengths of the actuator, the number of peaks between the restraint plates, and initial length of the EFPA peak when no pressure is applied. The shape of the EFPA can be determined using these empirical formulas. Based on calculation using the model, we design the actuator. Next, I will show you the pipe inspection robot based on the result. The right figure shows the transient view of traveling motion of the tested EFPA with actual elastic rigid restraint in pipe. In the experiment, a supply pressure of 500 kPa was used. The on-off valve turned on and off once. You can see that by automatic switching motion for coiling and extension based on axial elastic rigid restraint, the tested EFPA can travel in both these standard pipes. This study can be summarized as follows. We can confirm that the tested EFPA using wire winder can realize to extend after coiling. The analytical model of the EFPA was also proposed. The spring constant of axial restraint and rubber tube of EFPA that can realize the desired extension after coiling was identified. Thank you very much for your attention.